In this lesson, we will take all the counting techniques that we've learned up to this point and use them to define probability. To help us understand these definitions and ideas, I'd like to look at a very simple example, and that is, let's run the following, what I'll call a probability experiment. That is, a fair coin is flipped once. Without looking ahead to all of this, what happens if you flip a coin once? What are the outcomes? Well, you could get heads. That's a possibility. Maybe you could denote that by the letter H. Or the other possibility is tails, which you could denote by the letter T. It's either one option or the other. And because this is a fair coin, what that is indicating that it's equally likely that either of these things will happen. So you could say, well, 50% of the time, it'll come up heads. And then 50% of the time, it'll come up tails. And that's it. We've analyzed this experiment. So let's use this thing to go over a few definitions, starting with something called the sample space. The sample space is the set of all possible outcomes from the experiment. So using this experiment as a guide, I'm going to let the letter S stand for sample space. I'm going to put an equal sign, and the way we write a set is with a curly bracket. So I'm starting my set, and inside this set, I want to put all the possible outcomes. And there's two. There's heads, comma, tails. I close the set with a curly bracket, and that's it. So here's a set. It contains two things, the only two possible outcomes from this experiment, and I'm using the capital letter S to represent sample space. So this just tells you everything that can possibly happen. Nothing else can happen if you flip this coin, so this is it. Also, you can let the letter N stand for number, and you can say the number of things in S, in this case, is equal to 2. There are two outcomes in the sample space. Okay, so next, an event is a subset of the sample space. What does that mean? I'm going to use the letter E to represent an event. You can also write this as a set, so I'll put an equal sign in this curly bracket. And then inside of here, you can take some number of things from your sample space. And I'll take just one. In fact, I'll say heads. And I'll close it on the other side. And here's a set. It only contains one thing. You would read this as the event that you get a heads in this experiment. So a subset is just some collection of the things that appear in here. It could be all of them, but it can be less than that too. Oh, maybe I'll write down the number of things that are in the event. Is this the number of things inside the set? And there's only one, so the number of things in there is equal to 1. Now we come to a formula that we use to define probability. The theoretical probability of an event, that is, the likelihood that this event will happen, is defined as, we write P of E to represent the probability of event E. It's defined as the number of outcomes in event E divided by the total number of outcomes in the sample space. This thing here is the same thing that you would use to define percents. It's a part out of the whole. So here when you say a subset, it's some part out of all possible things that appear here. Now, I know this event should happen 50% of the time. Let's just use this formula to make sure that it matches up with this number here. So with the event that I defined, P of E, it's equal to the number of outcomes in this event, N of E, and there's only one of them, and it's divided by the total number of things that can happen, which is 2. And your probability that event E happens is 1/2. And if you'd like, you can write that as 0.5 if you prefer a decimal. Does this match up with 50%? Definitely. You'd have to convert this into 8% by multiplying by 100, and you, in fact, do get 50%. So this formula matches up with what I expected here. One important thing to note is when you say probability, we mean a number between 0 and 1. You can always convert them into a percent by multiplying by 100, but I'm just going to note that in general, if you find the probability of any event, it's always greater than or equal to 0, and it's less than or equal to 1. And the reason for this is these numbers correspond to 0% and 100%, which makes sense. So when we say probability, we're talking about a number between 0 and 1. You could convert them into a percent later if you wanted to. One other note, sometimes we'll look at multiple events depending on the experiment that we're working with. So there aren't a whole lot of options here for this particular problem, but if you have multiple events, you can use an E with a subscript to distinguish one event from another. So like E1 could be the event that you get a heads, and then you could let E2 represent the event that you get tails. So in the cases where you have multiple events happening in one particular example, you can use subscripts to distinguish between those events. All right, let's see if we can apply these ideas in the next example. In example 1, for all you D&D fans, a 12-sided die is rolled once. Find the probability of the following events. I think a good starting point would be to define what the sample space is if you are rolling a 12-sided die once. And you guessed it, you can roll a 1, a 2, a 3, a 4, a 5, a 6, 7, 8, 9, 10, 11, and also a 12. And that's it. Those are the only outcomes when rolling a 12-sided die. So in part A, here we have our first event, rolling a 9, and I'm going to call that event E sub 1. And what we're looking for here is the probability of this event. So the probability that event E sub 1 happens is the number of things that are in this event divided by the number of things that are in the sample space. I think it's worth noting, in this sample space, no surprise, there's 12 outcomes. You can get a 1 through a 10. What are the number of things in E1? Well, there's exactly one thing. You can roll a 9. It's definitely a subset of this set if you just took this one thing. So to get your probability, you would take the number 1, the part, and divide it by 12, the whole. And this is it. 1/12 is your probability. You could write this as a decimal, and I have my calculator here. If you were expressing it as a decimal, you would have to round. So it's approximately 0.083. That's a good probability. So as a fraction, this is exact, 1/12. As a decimal, approximately, it's 0.083. If you want to write this as a percent, that's not a probability, but if you change it to a percent, that would be about 8.3% of the time. Let's do that again for part B. Rolling an odd number, and I'll call this event E sub 2. We're still using this formula of the number of things in here divided by the number of things in here. So I know we're always dividing by 12. The question is, how many things are in the sample space for E sub 2? Well, it's a subset of this set, so I just need to count the number of odd numbers from here to here. 1, 2, 3, 4, 5, 6. That's it. There are exactly 6 of those things. Therefore, when it comes to finding the probability that event E2 occurs, that you roll an odd number, there are 6 possibilities in the sample space, and there's a total of 12 things in the sample space. So 6/12. This should always be simplified. 6 goes into 12 twice, so this is really a half. Or you could write that probability as a decimal, so 0.5, which is also 50% or half the time. So that makes sense. If you roll an odd number, it's half the numbers in this set. It'd be the same thing if you rolled an even number. That's the other half of the numbers in this set too. C says rolling a number greater than 9. So I'll call this event E sub 3. And again, the real trick for this problem is, well, how many items are in this set? Okay, numbers greater than 9. So you can't include 9 if you're greater than it. So we're talking about 10, 11, and 12. I actually think it might be nice for this problem. This is not always necessary, but you can write down what the set is if that helps you. So numbers greater than 9 that are in this set are 10, 11, and 12. And actually seeing them is nice because that means the number of things that are in this set is 3 things. Therefore, if you want the probability of event E sub 3 happening, it's 3 divided by 12. Again, this should be reduced. That is 1 over 4 because 3 goes into 12 4 times. As a decimal, that is 0.25. So that's 1/4 for your probability, or you could say 0.25. And that's the same thing as saying 25% if you convert that probability into a percent. And we're at our last part. This one says rolling a number greater than 14. So I'll call this first part here, I'll call that event E sub 4. So this is strange. What is in this set? It's got to be a subset of this. So you're only allowed to use stuff that's in here. But if you're greater than 14, you actually don't get any of this stuff. I mean, I'm not even sure. I guess you'd write it like this. It's the set that contains nothing. And there is a name for this. You can call this the empty set because it contains nothing inside of it. How many things are inside this empty set, the set that contains nothing? You guessed it, 0. There are no things in there. In fact, this is impossible, right? I mean, if you have a 12-sided die that is only ordered 1 through 10, you can't get a 15, a 16, a 17. You can't get any of those things. The good news is it does match up with our formula for probability. The probability that event E sub 4 happens is 0 out of 12, and this reduces to 0. So your probability is 0. It can't happen. And that's also as a percent, 0%. Now there's also this question in part D. What about rolling a number less than 14? So I'll call this second part, I guess, E sub 5. Well, if you're less than 14, that means, well, you can't be 13 because 13 is not in the set, but everything in this set is less than 13. In fact, E sub 5, this event, it's the same thing as the sample space. They're one and the same. And for this reason, the number of things in this set is equal to the number of things in the sample space, which is 12. So what is the probability of event E sub 5? Well, the number of things that can happen in the event is 12. Out of a total of 12 things, that's 1. I think it's nice to write this one as percent from a probability. That's 100%. And that makes sense with the way this question is phrased. Anytime you roll a 12-sided die, you will always get something less than 14. Every single time, 100% of the time, this is going to work. However, 0% of the time, that's not going to work. Again, just to distinguish, probabilities are not percents. You can convert them to percents if that helps, but I'll leave them in their decimal form. Another popular item for describing probabilities is a deck of cards, and I have all the choices in your standard 52 deck of cards listed here. There are a total of what are known as suits. There's 4 suits. There's spades. I guess I'll write this off to the side. You have spades. That's a suit. Hearts. Diamonds. And clubs. Those are your 4 possible suits. And for each suit, there's 13 cards. There's an ace, 2, 3, all the way up to 10. And then jack, queen, king. And that's it. In example 2, we're told that 1 card is dealt from this deck. And we'll assume that it's a well-shuffled deck so that this will be a randomly dealt card. What is the probability of being dealt a 7? A good starting point for this problem is, well, what's the sample space, which I've been calling S? You don't always have to write out the sample space if it's abundantly clear to you what that is. And I'll write it like this. What's the sample space? It's all of this stuff. These are all of the possible things that could happen. It's any one of these cards. And for this reason, the size of the sample space is 52 because there's 52 cards. Okay, on to our first event. the probability of being dealt a 7, and I guess I'll call this one here E sub 1. That is our first event. How many ways could this happen? So let's just jump to what is the number of items from the sample space that are in this set? Well, where are the 7s? They are here. Here are all possible 7s. There is 1 7 for each suit. So if you actually wrote out what E sub 1 was, you'd say, well, it includes the 7 of spades, 7 of hearts, 7 of diamonds, and 7 of clubs. That's it, a total of 4 things. So I'll just put, here's the size, the number of things in the set E1. If I want to know the probability of E sub 1, we have everything we need to answer this. It's the part out of the whole. It's 4 things in E1 divided by 52 things in the entire sample space. I think 4 goes into 52, right? Yeah, 13 times. So this reduces to 1 over 13. That's an exact answer. A 13th, I'll type it in my calculator. That does not have a great decimal, but if you're rounding, you could say it's 0.077 approximately. If you are looking for an exact answer, this fraction is nice. If you just need a simple approximation, you can write this as a decimal. I still do like to think of it as percent. This is 7.7%. So that's the likelihood of being dealt this card if the deck is shuffled. What's the probability of being dealt a spade? So I'm going to let that thing represent event 2 if you are dealt a spade. So for that event, for E2, being dealt a spade, what is the number of things in the event? So when we're talking about spades, we're talking about all of these things in this suit. And that's a total of 10, 11, 12, 13 cards. So there are 13 things in this event. And this makes finding the probability nice if we know the formula. The probability of event 2 is 13 out of 52. Without a calculator, I do know what this simplifies to. There's 13 things for each suit, and you're taking one of them. That's a fourth. So, you can even check this in a calculator. 13 goes into 52 4 times. So, yeah, this is 1 out of 4, or as a decimal, 0.25. There is a 25% chance that you will be dealt a spade, any spade. But that makes sense, right? There's 4 equally sized groups. I would expect 1 out of every 4 times being dealt one of these things here. And last one here, the probability of being dealt a 7 of spades. Okay, so for this last one here, I'll call this E sub 3. So again, we had E1, E2, and E3. What is the number of things in this subset? Well, this is a specific card. It is this one right here. There's exactly 1 7 of spades. Therefore, there's only one thing in this subset. The number of things in E sub 3 is 1. So the probability of E sub 3 is 1 out of 52. That cannot simplify. I don't think it has a nice decimal. Yeah, if you want to approximate this with a decimal number, you could put 0.019, which is, about 2%, almost 2% chance that you'd be dealt that card. Here's the exact value. Here's a rounded decimal, and those are the probabilities for these 3 events. In example 3, we have a diagram of a spinner. So here's the thing being spun, the pointer, and we have a total of 6 equally sized regions, meaning when this thing spins, the chance that it lands in any one of these regions is equally likely. So that is the first part here of example 3. And it goes on to say, if the pointer lands on a boundary between 2 regions, then we just kind of pretend that didn't happen. We just ignore it and then spin again until we do land in an actual region. If this is the case, Find the probability that the pointer lands on a yellow region. For this one, I think it is simple enough to reason out that, well, there's 6 equal pieces, and we're saying there's 2 of them that we're going to allow in the event. That would be 2 divided by 6. And that sounds great. I will still, though, write out what the sample space for this is. What is it? Could you say something like, oh, well, it's blue, yellow, and red. There's 3 things in the sample space. And this actually is a bit of a mistake. It's true that these are the 3 things that could happen, but there's 3 blue regions and there's 2 yellow and 1 red. So unfortunately, this really doesn't work. We have to be a little bit more careful here for the sample space. So you might want to do something like say, okay, I'll call this 1, 2, 3, 4, 5, and 6. And now your sample space would be, okay, we land on the 1st, 2nd, 3rd, 4th, 5th, or 6th region. This is just to make it a little bit more precise so it matches up with our intuition. So that first probability again was find the probability that the pointer lands on a yellow region. I can now more simply define this first event as, well, the yellow regions are 3 and 6. The number of things that are in this event is 2. There's a total of 2 items. And the number of things in the sample space is 6. Therefore, the probability of event 1 is 2 over 6. We should simplify this. This simplifies to 1/3. If you want to approximate this with a decimal, so 1/3 is a repeating bunch of 3s, you could say, all right, well, that's 0.333. That would be a good approximate value. So about 33.3%, or exactly, you could write 1/3 as a fraction. Okay, what about the probability that the pointer lands on a blue or red region? So this will be here. This is going to be event 2. So for event 2, the way we've defined it, if you land on a blue or a red region, you're allowing for 1 to happen, 2 to happen, 4 to happen, and 5 to happen. So that means there are exactly 4 things in this subspace of the sample space. Now, when we find the probability of event E2, it's going to be 4 over 6, which reduces to 2 over 3. If we use a decimal, it'll be approximate. That's about 0.667 or 66.7% if you want to convert it. So here we have a nice approximation, and this would be the exact answer. Before moving on, I'll remark on one thing that will show up in a future lesson. I defined event E to be the probability that we land here or here. What does it mean if we take the event not E1, meaning that this did not happen? Said another way, that means we are not landing on a yellow region. So you're not getting a 6 or a 3. What does that mean, though, if you're trying to define that event? So if this didn't happen, well, that would mean you could have event 1, 2, 4, or 5. And what do you know? That's actually equal to event E2. So not E1, the way we've defined things here, is E2. What does not E2 mean? So what if this event doesn't happen, meaning we didn't land on a blue or a red region? Well, that means you landed on a yellow region, which is exactly the event E1. Sometimes when computing probabilities, it's nice to consider not the event. In some cases, that can actually be an easier thing to solve for. So we'll expand on this idea in a future lesson. Now that we've looked at some basic examples using probability, let's expand on this to a few more complicated and involved examples. So here in example 4, we're told that Matt, Eric, Sarah, Mihail, and Juan are attending a party, and we'll assume the order in which they arrive is random, and that they're arriving at different times. Well, first of all, in how many ways can they arrive? After that, In how many ways can they arrive if Eric arrives first and Juan arrives last? And then what is the probability that this event actually happens? Let's start with this first question, which is not even a probability question. In how many ways can 5 people arrive at a party? The way I view this is, well, there's 5 people. So let's see, we have 1, 2, 3, 4, 5 spots. And the order here is important. There's a first, second, third, fourth, and fifth spot. There's a person who arrives first, second, third, fourth, and fifth. What did we use to count things where the order matters? Was that combinations or permutations? Well, here this is a permutation because the order is important. Basically, we're saying we have 5 items, and I want to know the number of ways in which I can permute them. So to reiterate, this is a permutation. Now, there was a complicated formula for this. There was n permute r, but here we're including all 5 items, and you can simply say it's 5 factorial. And that's 5 times 4 times 3 times 2 times 1. That is 120. This is the total number of ways that these 5 people can arrive at a party in a particular order. Okay, now what if we alter the question a little bit and say, well, in how many ways can this happen where Eric comes first and then Juan arrives last? So I look at this as, okay, now we have the same 5 spots, but Eric is here and Juan is here. And in the other 3 locations, in the second, third, and fourth spot, we want to somehow be able to count the total number of permutations of just those 3 people. So there's 1, 2, 3 places that we are permuting, and the way to compute that is 3 factorial, which is equal to 6. With the 3 other friends, there's a total of 6 ways that you can arrange them so the order in fact matters. So the first one was a permutation of 5 items. And here, this is now a permutation of only 3 items. So far, these are just counting principles that we saw in the previous sections, nothing yet about a probability. But now, the last part says, find the probability that Eric arrives first and Juan arrives last. So the probability that this event happens. In fact, if you want, you can call this thing here event E1. So I'll define that. This is event 1. It'd be helpful to know the sample space, or at least the size of it for that matter. What's the sample space? The sample space is all the possible ways that people can arrive to the party. If you actually went through the process of listing every way these 5 people could arrive, that would be your sample space. So it's every way that these things can be listed. At this point, we can now go back to our formula for probability of an event. It's the number of ways that the first event happens divided by the total number of items in the sample space. What are these things? Well, they're precisely what we computed up here. If this is the entire sample space, the number of ways 5 people can arrive at the party, this counts them. We didn't actually have to list them all out, but there are definitely 120 ways. So that's going to be the number in the denominator, 5 factorial, or 120. For this event to occur, if Eric is first and Juan is last, there's only 6 total ways that you can list this out because we're permuting 3 of the people. And I'll just put the number 6 in the numerator. So this is not simplified. I think 6 definitely goes into 120. In fact, it goes in 20 times. If you reduce this fraction, it is 1 over 20. As a fraction, this is the probability. If you would like to express this as a decimal, you could divide it. And when you do, you get 0.05. If you prefer to think of this as a percent, this is a 5% chance. But here, since we're asked about the probability, you can either write 1 over 20 or even exactly 0.05. In example 5, we're told that a hand of some card game consists of 3 cards from a shuffled deck of 52 cards. First, I want to find the total number of possible 3-card hands. So here we're counting. Now, this could either be a combination where order does not matter, or it could be a permutation where the order that they're dealt does matter. Let's think of a possible 3-card hand. Like maybe you have an ace of spades. So you could have an ace of spades. And then maybe the second card that you are dealt is a 4 of diamonds. And then maybe the last card you are dealt is a king of hearts. So here's a possible 3-card hand. Now, if this were talking about permutations, we'd want to count this hand different than the following hand. If you were first dealt a king of hearts, a 4 of diamonds, and then an ace of spades. So what do you think? In this problem, should these two things be considered as different hands, or are they the same hand? We want to count these as the same. These are the same hand. Because once you're dealt the cards, you can just shuffle them in any order you want. The order is completely irrelevant. And this, to me, says, since the order does not matter, we are talking about combinations. We are not talking about permutations. There was a formula that we had when dealing with combinations. I'm going to state it here. That was n choose r. The formula for it was n factorial divided by n minus r factorial times r factorial. Now let's move on with the question here. We want to find the total number of possible 3-card hands. We can directly go to this formula to figure that out. There's a total of 52 cards that we can choose from, and we're picking 3. What's the number of ways you can choose those? That would be defined as 52, choose 3. I can now put this information directly into the formula. This is 52 factorial, which is an enormous number. That is divided by 52 minus 3, and then we take factorial of that, and then we divide by 3 factorial as well. Okay, we want to simplify this thing. Looking at the fraction, I'll leave 52 factorial alone. 52 minus 3 is 49, and it's factorial, and then we have 3 factorial. Aha. 52 factorial means 52, 51, 50, and then 49. I'm going to just make a note down here that 52 factorial means you can start at 52, multiply to 51, to 50, and the second you get to 49, that's just factorial. I can replace this with this and cancel the 49 factorials. Let's do that. Okay, that's 52 times 51 times 50 times 49 factorial, all divided by 49 factorial times 3 factorial. And the point of doing that was to cancel the 49 factorial. There's still a good amount of stuff left over. Kind of running out of room here, so I'm going to... Here, I'll put this up here. Okay, this is equal to 52 times 51 times 50. If we're dividing by 3 factorial, 3 times 2 times 1 is 6. At this point, this number is enormous. I'm going to do this in my calculator. 52 times 51 times 50. And that is, in the numerator, that's 132,600 divided by 6, which comes out to a lot. It's 22,100 ways that can occur. So this is the total number of possible 3-card hands from the entire deck. And so that was this part here. Now, this question goes on to say, it defines something. If a red flush is a 3-card hand and it consists of all red cards, can we find the total number of possible ways this happens? Okay, it's going to be a very similar process to this. This is every single possible hand that you could get. But what if it were just red cards? So I'll say, I'll put down here, I guess, a red flush. Like, how would that happen? Well, the red cards are the hearts and the diamonds. And you only want to choose from those suits. And there are 13 hearts and there are 13 diamonds. And if you add those together, you get 26. So in trying to count the number of red flushes, you're not choosing from 52 cards because that includes the spades and the clubs. You only want to choose from 26 cards, but you're still choosing 3. For this reason, to figure out the number in this next part, it's not 52 choose 3, it is 26 choose 3. And remember that the order does not matter, which is why we're choosing combinations. The formula for this is similar to what we just did. This time it is 26 factorial divided by 26 minus 3 factorial and then 3 factorial. I ran out of room here, so what I'll do is on the next slide, I'll copy down this number, we'll compute this, and the ultimate point of this question is, once we figure out the number of red flushes, we can ask the question, well, what is the actual probability that you'd be dealt this kind of hand? So from our previous slide, this was the total number of possible 3-card hands chosen from the entire deck. The thing we're going to compute here is going to be all possible red flush hands, meaning you're only dealt the red cards, of which there are 26 and you want 3. To simplify this expression, I'll start with this 26 minus 3. So we get that this is 26 factorial divided by 26 minus 3 is 23 factorial, and then we have 3 factorial. We've done this trick a few times. I think it's still worth writing out. 26 factorial is equal to 26 times 25 times 24, and then the rest you can write as 23 factorial. It's good to write that in order to cancel this thing. I'll swap this with this. So we got the numerator is 26 times 25 times 24 times 23 factorial. And that's all divided by 23 factorial times 3 factorial, meaning we can cancel the 23 factorial and we can call 3 factorial 6. So this whole expression is 26 times 25 times 24 all over 6. Again, pretty big number. I'll do that in my calculator. 26 times 25 times 24. That's 15,600 in just the numerator. And if we divide that by 6, we get 2,600, 2,600. So out of all possible 3-card hands from the entire deck, there's 9,100. The total number of all possible red flushes is this amount. The last part of this problem was asking us, what is the probability that you will be dealt a red flush? So the first 2 parts of this problem were setting up the answer for us. Essentially what we're going to do is to find the probability that you get I'll just call it a red flush. The probability that this happens is the number of ways a red flush can happen, that's 2,600, divided by the total number of hands in the entire sample space, which is 22,100. Okay, I mean, here it is. This is the probability. It's just not written in a nice way. I'm going to try dividing this in my calculator. So 2,600 divided by 22,100. I get 2 out of 17. So write that over here. The probability of being dealt a red flush, not a percent, but a probability, the fraction reduced to 2 over 17. And if you want an idea of the decimal approximation, which can be helpful, this is about 0.118. So if you want to think of this as a percent and not a probability, that's really 11.8%. So, not super uncommon, but also not very likely. So this was the ultimate goal of the problem, to find this particular probability of being dealt this kind of hand. And we need to use a very sophisticated counting argument to get there. We had to use these formulas to figure out these numbers, but once you know those numbers, all we're really doing is just dividing them. In our last example, it says if you are dealt 3 cards from a well-shuffled deck of 52 cards, what is the probability that you are dealt 3 hearts? If you'd like and you're feeling comfortable with this process, what we're looking for is the probability of the event being dealt 3 hearts. I mean, it is okay to start here if you understand the fraction that you're looking for. In the numerator, this is going to be the number of ways that 3 hearts could be dealt to you. And then in the denominator, this is going to be the total number of 3 card hands that you can be dealt. So just like in the last problem, is this a combinations problem or a permutation problem? This is combinations. We don't care about the order in which the hearts are dealt to us. We just want 3. And for this reason, we are again using the formula n choose r, which was n factorial divided by n minus r factorial times r factorial. That's what we want to use. So in the numerator, what's the number of ways that you can be dealt hearts? Well, there are 13 hearts and you want 3 of them. So within the numerator, we want 13 choose 3. What is the total number of 3 card hands? Well, this is not just from the hearts, but this is from all suits. And for this reason, that is 52 choose 3. It is this fraction that we'd like to simplify. So we could go through these computations and get numbers for them, and then at the end, we'll divide them. I'm going to start with 13 choose 3. That is 13 factorial divided by 13 minus 3 factorial divided by 3 factorial. In the denominator, 13 minus 3 is 10 factorial. I'll leave the 3 factorial alone. Since we've done this a few times now, 13 factorial is 13 times 12 times 11. And then once you get to 10, just call 10 factorial. This way we can jump to canceling the 10 factorials, and they're just 1. 3 factorial is equal to 6, so this is 13 times 12 times 11. 3 times 2 times 1 is 6. I'll do this in my calculator. 13 times 12 times 11, that's 1,716. Maybe I'll put that down here. 1,716, all divided by 6. That is equal to, let's see, 286. There we go. That is the number of ways that we can be dealt 3 hearts. That goes here. That's the part out of the whole. 52 choose 3. Actually, we already did the computation in the previous example, right? I think for 52 choose 3 in the last problem, it was 22,100. I don't think we have to go through that again. It was just on the previous slide. I'm just going to go ahead and plug that number into our formula. This is the total number of 3 card hands. All right. So in the numerator of this fraction, that is 286. In the denominator, that's 22,100. And that's our probability. Probably got to simplify this. So I'll divide it in my calculator. Let's see. Okay, 286 divided by 22,100. The fraction I get reduced is 11 out of 850. So the part to the whole. I can't reduce that anymore. It might be nice to see that as a fraction. Sorry, as a decimal. Yeah, this is not very likely. This is approximately 0.013. So you could say 1.3% of the time. I was not expecting this to be a likely event. In fact, this is a small probability with a small corresponding percent. But that's how you compute it, and that's it for this example.